Hello everyone. So I am Rohit. Today we have an assignment that we can discuss. So this is about an hybrid CPU scheduler. So what's a CPU scheduler? A CPU scheduler is basically generally in a chip you have multiple processes to finish. So how would a chip efficiently take each of the process and finish it on the time? That's the whole idea of the CPU scheduling. So it's not like multiple CPUs will be executing, that will be easy. But with a single CPU, how it will do multiple process almost fast. So that's the thing. So in so here, if you take an example, so let's imagine that this is the CPU, and then this is a queue. There's a queue over here, and in the queue there's P1 that would have came at time 0. Then there's a thing P2 that came at time 3, then P4, P3, then let's say P5 for example, then later comes P4. So it can come in any order, that's the thing. And now each of these process won't take the same time. It will be different time. It will vary according to the process. Some process may need only 3 milliseconds, while some process may need 10 milliseconds, while some may just have like 0.5 millisecond. So there will be different process will have different thing. This we call it as burst time. We call this parameter of a process called as burst time. Again, arrival time can change because we are arriving at different time. That is called arrival time. Okay, this is the thing. Now beyond this, we have two more things. One is the priority. Whether is this more priority if P2 is more priority or if P4 has more priority or if P3 has. So how do you represent that? With numbers, of course. So we can tell P2 has a priority of 1, meaning that has to be executed first. Even if it's not standing in the queue, it has to be executed first. So you can consider this something like a VIP, it's like a very important person. It has to be executed first. Not a person, very important process VIP. Okay. Now let's take the next VIP is P4. So what the CPU does, because I get the priority here, the CPU may consider will take the P2 first. So now the P2 will be doing the CPU work. In the queue, there'll be P1 left, then there'll be P3, and then there'll be P5, and there'll be P4. Now, after P2 finishes work, it can go to P4. P4 can be in the CPU. Okay, sorry. Yeah, P4 will be in the thing. Well, P1 remains. P1, P3, P5. So this is one more thing. So there's another priority called priority. Okay. Finally, the type of activity, the type of process. The type of process may change. Type of process can be real time, which means it has to happen simultaneously. It has to happen as soon as possible, like spontaneously. Another is interactive. Interactive comes under real time, but it doesn't need that much. It doesn't need to be alive. It just has to work on the time. Finally, batch. Batch is it has to finish the full process completely. That's the whole idea of batch. While interactive is like somewhat between in real time and batch. It's somewhere between. That's what interactive is. Okay. Okay. So these are the four parameters. So this is one parameter, two, three, and four. So based on this, there are different ways to schedule a CPU. So as I told you, there's one way. One way is for with the technical shortest job first, meaning um, so here what is that? So here we told that this is the this will P3 will take 0.5. So we can tell it, okay, finish the P3's work because it's very less. It has very less time. Let's finish it first. Then we can go with P1 because P1 is the next least. Then we can go with P5. So like this, that's the technique. That's a technique called shortest job first, meaning do the easier task easy first. That's the idea. That's one technique. But the problem is tasks that are very long. Example, take P4 is like some 50 millisecond. It'll be done towards the end. So at the end, so like it'll take, even if it came the first, it would have been towards the end, which may lead to a concept called starvation because it's literally starving. Like you're not you're not allowing it to do its work. It's just making wait, and do it. Like imagine like you don't get to eat, and then at the end of the day you eat. So that's like you kind of starve. That's the whole idea about this. So in all the CPS scheduling, there's starvation that we cannot eliminate. So that's the thing. So this is based on the burst time. So we can keep it BT. Another thing is FCFS, first come first serve, meaning this doesn't care about how long your process is or what's your priority. If you come first, you'll get your job done, or else you won't get. So this is based on arrival time. Finally, the third one is priority. Okay, priority is again based on priority, like how I showed over here. The one that has more priority, even if it comes later or even if it has a short, longer burst time, since it's given priority one, it has to do it. That's the whole idea of priority. That is based on priority. So these are the traditional CPU scheduling techniques that we can use. But as I told, each has its own drawback. So that is not what I'm going to explain. So what I'm planning to explain is I'm planning to give a solution called a hybrid CPU scheduling. Hybrid CPU scheduling is, as the name defines, it's going to consist a little bit of everything. Okay, not everything. It is, we won't be using first come first serve here because the first come first serve technique is very vague. It's not that useful because just because you came first, that it doesn't work. So what we're going to do is we're going to have a mix of three things. One is, of course, as we know, there'll be a shortest job first. We will want to like finish the shortest job first. Then we'll be using another CPU scheduling called round robin. So what does round robin do? Round robin is basically you work on each process for a certain number of time quantum. So tell the time quantum 3 millisecond means P1 will do for 3 millisecond. Even if the P1's work is not yet over, after 3 milliseconds, it will switch to P3. And P3 will do for some 3 milliseconds. After P3 is done for 3 milliseconds, it will switch to P4. So it'll keep going on. It'll be going batch by batch. Okay, so that's one thing. So for an example, you can take a teacher who's correcting this paper. So she can correct each first question of every single paper, then go to every second question for every single paper and go on so on. So that's called round robin. So you go each. That's the idea of round robin. So that's one thing. Finally, this is kind of like a priority thing, but what we use is the priority. So we're using these three CPs today. We are creating hybrid solution. So how does this hybrid solution work? So as I told you, we have these four parameters. Okay, arrival time is not going to be much of an issue here. It doesn't matter. It can be the same thing also. But let's just keep that for now. So we'll go one by one. So first, let's take priority. So as I told you, real time needs to be done on spot. It should be monotonously done, spontaneously done, right? So when if it's a real time process, it is a real time process in the queue. Okay, like here one of these process, like take P3 for example. P3, if it turns out to be a real time process, that should be executed first. Okay, but here's the catch. It may be even at P3 and P4 are real-time process. So what do we do that? We go by priority base. So first is real time. We'll give preference to real time. Within real time, we'll sort based on the priority. That's our idea. So it'll execute a real time process with the highest priority first. Okay. Now we go to the next one. Second one is using the shortest job first. So now by this time we'll know that if real time is not there, if there's no real time in the queue, then it should be either interactive or batch. Okay. So let's just take interactive for now. So interactive means what you should do is interactive in the queue means Sorry for my bad handwriting. Yeah. Interactive in the queue means it has to do round robin. Because here, again, here's the thing. Interactive is between real time and batch. So each are given the same, all the processes that have the interactive type should be given the same amount of work. So we're going round robin so that we'll give equal amount of time quantum for everything. So we're going for round robin if it's interactive. Interactive, again, the thing is that there should be no real time at this point. The whole queue should only have either interactive or batch. That's the whole idea. Now the third option is if there's only batch in it, only batch, only batch in the queue. Only there's batch, meaning all the real time and interactive is all done. Only batch left. Batch processes, as the name says, it has to be done in batches. So for this, we can just go with the shorter job first. We're just going to take the um, we're going to take the shortest job and finish it first. That's the whole idea of this thing. Okay. So this is the example. This is the type of hybrid CPU scaling I'm going for. So again, the logic is simple. If there's a real time in the queue, do finish all the real time processes. And if there are multiple, they sorted by priority and do finish it. Then if it's interactive, only interactive, meaning there's no more real time, it's only interactive or queue. Take all the interactive processes and create a round robin for that. Finally, if you have only batch processes in the left, do the shortest job remaining. Okay, that's the whole idea for this thing. This is the thing. So now I'd like to explain the code as I continue. Yeah. So here we're back to the code. So we'll take these things. So I'm going to use a Python for this whole thing. So first we'll define a class called process so that we'll take all the things. So here all the variables are self-explanatory. There'll be a process ID, then arrival time, burst time, remaining time. So initially the remaining time will be burst time because it will need the remaining time to finish a process will be equal to the burst time. Then the priority, then the type of the thing, if it's real time or interactive or batch. Then finally start completion is for the calculation part. Okay. And now for our purpose, we'll just take this for example. So let me just draw a table for it. In this table, as you can see, so how to represent this whole thing, we can do using a thing called Gantt chart. Okay, so that basically it will capture what's going on from time zero till the time end. Okay, so it will look like kind of like a queue, but it's not a queue. So we'll take this. Okay, so it starts at zero. So at zero, the only process that's available is P1 because only data is arrived on time. So we'll just use P1. Okay. And notice that P1 is a real time. So it has to be executed. So P1 will be executing until time 1. Okay. Now at time 2, P2 also is arrived. Actually, P2 is arrived. But the thing is, P2 is an interactive based. It's not a real time. So we will still be giving preference to real time. So we'll still be giving the preference P1. So P1 will go till um, 2. Okay. And again, as you notice, at P3 also, this is given the thing. So again, this will also, this has to go. Meanwhile, at the same time, what happens is, let's imagine this is a queue. Okay. So now there's a P2 inside a queue. So initially there's no queue. Now there's a P2. And from 2 onwards, there's again from 3, there's another, no, there's another thing called P3. So P2, then P3. Okay. And then again at P4 comes another thing. So this is also real time. So now there's a real time and a real time. But if you see the priority of this is greater than this. So we have to give priority to P1. So P1 will still continue doing its task. So it will go to P4. And now in the queue there's Since P4 is real time, this will be give more preference. Then comes P2, then comes P3. Okay. Now fourth time P5 will occur, but this is interactive, which has nothing to do. So this will still continue. So P1 will still continue till 5. Then so the Q node will be a P4, there'll be a P2, there'll be a P3, and there'll be a P5. Okay. So now here's the thing. So while they're doing this, if you remember, I told you there's a thing called starvation that happens. There's a thing called starvation because something will keep waiting. So what we can do is we can do something called aging. So basically, what aging does is, as time goes, if something has been waiting in the queue for a long time, it will reduce its time. It will reduce its priority. Like the priority of it will be increasing. So here, for example, P2, as you've seen, it has been waiting for 4 seconds. So 4 into a particular threshold. So here I took threshold as 0.1. So I took 0.1 equals 0.4. So now what will happen is, if you take the value P2, P2 before 3, now it's going to reduce to 3 minus 0.4, which will make it 2.6. Yeah. So it'll make it 2.6. Okay. So now what will happen is P2, which has been waiting for it, will become now 2.6. So it's 2.6 here. And yeah, P3 also has been waiting for 3 seconds. So 3 into 0.4 is 0.3. So P3 has been waiting for, so 5 minus 0.3, which will make it 4.7. So this will become 4.7. So the priority will keep decreasing. This you have to keep in mind. And 5 it has only waited for 1 second actually. So it'll just go by 1 point. So it'll just be 3.9. Okay. Okay. And 2 has waited for, so P4 has been waiting for 2 seconds. So that will go down by, so this will become 1.8 actually. Okay. So now, even now also, we have to consider real time. So here the real time is still these two only, P1 and P4. And on the other hand, the remaining time for P1 is now currently 3 because it has already done for 5 seconds, 5 milliseconds. So still we'll be giving priority to P1 only because it has done this. So let's just consider the P1 has done all the full 3 seconds. So it's gone all the way till 8. Okay, at this point, all of this will be reducing by 0.3 because all of this has been waiting for a queue for a long time. So this will become 2.3. It's going to become 2.3. 2.3. This is going to become 4.4. It's going to become 1.5. This is going to become 3.6. Cool. And the queue will still remain the same. P4, then comes P2, then comes P3, then comes P5. Okay. So now at this point, what happens is, yeah. So now that P1 is done, P1 is completely over actually. So now this is becomes 0. So now on P1 doesn't need to do anything. It's completely done. So I'll just mark this to show that it's done. You don't have to worry this anymore. So now the next thing important is a real time because the next real time is P4. So P4 will be in the queue now. And as you can see, I don't think there will be any priority change. It will always be real time first. So this will be doing for next 4 seconds. So till 12, it will be P4 only. So that means there for 4 seconds. So 4 into 0.4, 0.4. Okay. So this for aging purpose. I'm telling the aging purpose. So now what will happen is This will become 1.9. On the other hand, this will become 4. P4 is in the thing, so this won't age anymore. There's nothing called aging here, but this will age, so this will become 3.2. Okay. So now what will happen is, so yeah, this will also be done fully. Real time is fully done because that's the only thing in queue. That's the only we have to give priority first to real time. So now in the queue, what will remain is it will be P2 with followed by P5, then followed by P3. Why this change is because P3 is a batch. P3 is one batch, so it will always be executed end. Whereas P2 and P5 are interactive, so they have to be. Now, as I told, for interactive, we decided to do the following. For interactive, I decided to do round robin. Okay, so from now on, it'll just be round robin that's going to happen. So how round robin works is it took a time quantum of 3 milliseconds. Meaning what it'll do is it'll do a process only for 3 milliseconds and it'll stop. So now a P2 will start. It'll do only till 15. So here what's happening is P2, even though the burst time is 5, it'll only do for 3 seconds. So there's the remaining 2 seconds left. So now in this thing, it'll become P5 followed by P3 and that's all. Okay. And again, 3 seconds is gone. So now in the rest of the stuff, this will become 3.7. On the other hand, P5's priority will become 2.9. Okay. Now next is again you have to take P5 because that's interactive. So P5 will do under the other task till 18. And in the queue, even though the P3 was there and it should be P3 followed by Q2, since P2 is interactive, P2 will be in the queue again. Then comes P3. Okay, so again, now again there will be a starvation, there will be again aging that will go on. So since it is this, so this will go by zero point 0.3 again. So it will become 1.6 at this point, and this will become 3.4. Okay. And again, this one also would have done 3 seconds fully. So now we'll have this one. So now P2 doesn't have to work for entire 3 milliseconds because only thing that's left for it is 2 milliseconds. So it'll just do for 2 milliseconds. So P2 will do only till 20. Okay. And then now in the queue there'll be only P5 and P3. And again, since so P2 is done fully, so we can just mark it off, make it 0. So I'll just make it 0. Okay, it's 100. Okay, so now next is P5 because that's an interactive base. So P5 will take P5. And this will be doing for rest of the 3 seconds. So it will go up till 23. Okay, so till 23 will do. While in the while in the Q will be only P3. Again, again it will go for aging. So this will become 3.1 at this point. Okay, and then P5 has done its work fully. Okay, finally only P3 is there. So P3 will do the entire task on its own because the queue is empty. The queue is empty, so it will just do only by itself. So P3 will do for all the 12 seconds, so it will go up till 35. Okay, so this is the Gantt chart. The Gantt chart goes like this. Okay, so now based on this Gantt chart, what do we do is we can complete a table. We can find a calculation. We can find what's the thing. So we can find the average waiting time and average turnover. So first we need to calculate the completion time. So as we can see, for P1, it completed at 8 milliseconds. So it just goes for 8. Okay. P2 on the other hand finishes at 20. It already finished here once, but we have to consider it a last part. So this finishes at 20. Then comes P3, which of course finished at last solid, so 35. Then P4 has finished at 12. So this will go 12. And then P5 at 23. Okay, so this is the completion. Now for turnaround time, turnaround time is simple. Turnaround time is basically your completion time versus arrival time. So it is CT minus AT. So you keep them in. So it will make it 8 over here. Then it'll make this 19. It'll make this 33. This will become 9 and this will become 19. On the other hand, WT. So we just said is this. WT on the other hand is it's TAT minus BT. So it's the turnaround time minus the burst time. So burst time, turnaround time is 8. We have to take the initial thing, not the final remaining one. We have to take initial was 8 over here. So 8 minus 8, 0. 19 minus 5, 14. Then 33 minus 12, 21. Then 9 minus 4, 5. And 19 minus 16, 6, 13. Okay, so your average is basically sum of this divided by 5. So here you get to this 10.6 and here you get 11, 17.6. So here the thing is, this turns out to be very effective compared to your other scheduling process. Example, FCFS and the thing I said earlier, round robin. It's more effective than this. In the code, we can see it. So now I will explain the code further with so this is the Gantt chart. So this is the Gantt chart, and you'll be getting a similar output even in the thing. Okay, so that's the whole idea. So now coming back to the code, as I told you, we took this and we actually calculated the entire Gantt chart. Okay, which is useful. So first thing first, I'm cloning this because I want to run the same schedule. I want to run this different scheduling algorithms on the same type set of processes. So we have different processes. First is first come first serve, which will do exactly how it says. It'll sort it based on arrival. So here, as you can see, it will sort based on arrival. So it'll take the first one that comes in arrival and it calculates the whole thing. It'll calculate the completion time, the turnaround time, and the waiting time and all. Then next is round robin. So here I get q equals to 3, which is your time quantum, how long it will be working. So again, that same thing. This is already there actually. This already exists. This is the same code that we did earlier. But here, this is the thing I'm interested for. This is the run hybrid. This is what will do the hybrid scheduling thing. So first thing first, um, we are creating all the following. So first is procs, which is clone. It's basically you're like cloning all the process. So this process, this thing, but it's another version. It's not the same thing because we don't want to alter this after we run this one. So we just made it. Okay. Then we have a ready queue, which is a list for now. And we have also done list so that we'll know we can keep track of what is completed, what's not. Because if something is completed, we don't have to repeat the process again. And a timeline just to show for a Gantt chart. And finally added, then finally time and maximum time, how long you can make it go for. This to avoid the starvation part. So first thing first, as long as the number of items that are done is less than the number of remaining process, you have to keep doing this whole thing. So first thing first, go through the all the processes. Only consider the process that has happened before a current time. So T here is the current time. So first T will be 0, then become 1, 2, it will keep going on so forth. So only consider the processes that have arrival time less than the T because you don't want to worry about the things that will come in future. That's not needed for now. And also additional is you should make sure that the ID is not yet added. It's not yet in the set yet. So that's you can leave it. Okay. So first thing first, if all this works, push it to the ready queue. Push it to the ready queue. So I'm appending it. And after you do all this, if there's nothing in the queue, if nothing is in the queue means it has to wait. So we're just going to add 1 more millisecond of time and just continue. We're not going to do the rest of the thing. But in case if there's something in the ready queue, first thing first, do an aging. Like set an age for it. Like set which one, how long it has been. So as I told you, we get the threshold of 0.1, meaning as if you're doing x seconds, so x in the 0.1 seconds, it'll keep reducing the priority. And we just get made sure that it'll always be one. At max, it'll be one. So we're capping it one. So even if it's a one, after 1 millisecond, even if it's in the queue, it's not going to become 0.9. It's going to be still one only. So we're just capping it at one. Okay. Then finally, we're taking all the remaining bursts. So as here the thing is, we have to consider only the remaining burst, not the burst itself. And we're checking for the average burst. Okay. Then finally, we're checking if there's any real time in the process. So only if there's a real time in the process, immediately go with priority scheduling. That's the whole idea. So if there's anything in real time, I'm using any to find which and all is there, which and all is there. So the any real time in the any process which is real time, first order ready by the priority and pop the first one, first element in the list. So that you will do that. Okay. This is for this is the priority scheduling when it's a real time. Second is round robin. So round robin, as you told, this is the round robin part. So here we have coded the three as the time quantum, which is fine. So basically round robin is for all the interactive based. Okay. And again, as per my calculations, if the average burst time that's left is less than 6, it will most likely be a batch scheduling. So only for batch scheduling, you have to go by shortest job first. So unfortunately for our example, there's only one batch process, so we couldn't show the thing, but it'll work the same way. It'll take the shortest job and finish that first if it's a batch program. Okay. So you do all this. If something is not yet started, if the process is not yet started, make it start. Tell that it has started at time equals to 0. So if we take example P4 started at 5, so now the P4 it has to start at 5, so we just keep setting it as equal to 3. Finally, we're just incrementing the time, telling that this is there, and we're decrementing the burst time so that it will do. And if the burst time is become 0, the remaining burst time is equal to 0, it means the process is over. So we're equating it to T, we're making the completion time equal to T. And we're doing the calculation. As I told you, TAT is CT minus AT, and with WT is TAT minus BT. Okay. After all is done, push this into the done list so that you don't have to repeat this again. And or else if it's still not yet done, add it to the ready queue and continue doing the thing. So this is the whole thing. Finally, utilization is basically how much are you utilizing? Are you like wasting any space or is it continuously being utilized? So for our example, as you can see, there was no gap at all. We continuously utilize. So we'll be getting 100% gap utilization. Finally comes here. Here we're just printing the table to get the Gantt chart and all this. And we're printing the table to get the to show how it's calculated. Well, this is to print the Gantt chart. Okay. Finally, we are running all the three types of scheduling. First is first come, first serve, then round robin, then run hybrid, which is the one that we are doing. And finally, we are printing the table for each and printing the timeline only for the hybrid model. Okay. So now let's go to the output part. So hello. So now we'll see the output. So as you can see, yeah, as you can see over here, you can see that the first come first serve, you get an output of 13.0, which is the waiting time. The waiting time is 13.0, while the turnaround time is 20.0. On the other hand, if you take round robin, it takes a weighting as 17.8, while the turnaround time is 24.8, which is worse. But on the other side, if you look at the adaptive hybrid, it takes only a waiting time of 10.6. So this is like 3 milliseconds faster than the first come first serve. And again on the same time, turnaround time is again the least. So in many ways, this adaptive hybrid is better than the first come first serve and as well as round robin because this mixes up and dynamically changes according to the process schedule. And for the Gantt chart, because a little bit the primitive word itself. But here's the thing. So again, the same Gantt chart that we got, it's exactly the same. So I'll just try to keep it side by side for you guys to see. Okay. But exactly the same. We this goes each millisecond it checks, but we also mixed up, we just combine all together. But this works. Okay, so this is the whole idea. This is the code that I'm showing. Okay, so I hope this is helpful. This helps out hybrid scheduling. Real-time process, it will be very helpful, especially where you have to consider real time, you have to consider interactive based, you have to consider batch based. All this will efficiently manage. Okay, so thank you very much. I hope you enjoy this. Um, See you next time. Peace.